Hi, welcome to part 2 of our special series on Bose-Einstein Condensation with Dr. Carl Wieman. I'm Cameron Sahami, this is Kachun, and this is Moment of Science. Kachun, if you could reintroduce Dr. Wieman.
Yeah, well, Dr. Wieman is a professor of physics at the University of Colorado and also a fellow at JILA, which is a joint institute between CU and the National Institute of Standards and Technology. And he's here to talk to us today about Bose-Einstein condensation. And actually, this is really exciting work for a lot of people in the physics community, especially the physics department at CU, because I guess there's a lot of talk that this might be Nobel Prize winning work.
Yeah, we've heard you've been nominated for the Nobel Prize, so congratulations, Dr. Wieman.
But well, first of all, since this is a two-parter, I guess what we should do is start with a short recap of what we discussed last week.
Okay. Yeah, so what we're trying to do, and by we, I should say in the first slide, it's not just me, it's a whole team of students and postdocs, and we've been, quite a few of them over the years, working on this. A few of them are shown in the first slide.
Okay, so let's turn off the lights in the first slide.
And you can also see a little bit of the lab here. This is about half of the people who've been working on this.
Check focus.
Focus slightly. Yeah, and you can also see some of the apparatus that we use for making this. And actually, this team has sort of two leaders. I'm half of it. The next slide shows you Eric Cornell, who's the other one who's been working with me for now quite a number of years to actually make this. So you're saying, you can have the lights back on.
Lights, please.
What we've been trying to do is get atoms incredibly cold to achieve this new phase of matter. Just how cold we need to get is, if you can show the next slide.
Lights, please.
There's a thermometer here to illustrate the scale where Fahrenheit's over here, way down to about minus 460, so that's even colder than it was here last week. That corresponds to what we call absolute zero. Temperature is the motion of atoms, the speed of atoms, and this corresponds really to atoms all being completely stopped. We have to get down to about 10 billionths of 1 degree away from absolute zero to make this. So I talked last time about the first step. If I can go to the next slide. The first step is we take some atoms, a kind of atom called rubidium, and we put them inside this little glass cell here. This is about 1 inch on a side. We send in light from laser beams. You can see the red beams here going into this cell. And by bouncing that light off the atoms, we take them from room temperature down to about 10 millionths of a degree above absolute zero. So that's still 100 times too hot for Bose condensation, but it's incredibly cold by any normal standard and was actually sort of a record for getting things cold. If I can have the lights back on, I'll just...
So that's the coldest any substance has ever been?
Well, there's been, over the last decade that we've been working on this, people have been sort of setting records. We've usually been first or second along the way, getting colder and colder. So it was 100 millionth of a degree Kelvin, or 100 millionths of a degree above absolute zero back 7 or 8 years ago, and then we brought it down to about 5 years ago. We brought it down to just a few, like 1 or 2 millionths of a degree. And that stood as a record for quite a while, and that's actually what, at the point we got excited about trying to go farther to get Bose condensation. But let me show you then give you sort of an analogy to the way we slow atoms with laser light. If you magnify things way up, you imagine this is an atom, okay, that's been magnified up enormously. And that atom is going to be zooming along. Real atoms go 1,000 miles an hour. This one's going to be going a little slower because it's so much bigger. And you can think of these little ping pong balls here are like the little particles of light called photons that we bounce off the atom. So here's my laser.
This is my favorite part.
Yeah. You might remember this from last week, too.
Yeah.
We're going to do it again because it's
We're
so
going to have
exciting.
our atom zooming towards me, and I'm going to hit it with a laser beam and slow it down.
Okay.
Let's try a little faster than last week here.
Okay. Here we go.
Wow, it's pretty quickly.
Right to a stop. Nice and cold. Okay?
Wow.
Unfortunately, you can see it didn't totally stop. It was still moving a little bit. And so that was what limited us. And so we had to figure out ways to go beyond what laser light could do to actually get bosons.
So with laser light, you can't go below, say, 10 millionths of a degree.
So why is that? I mean, it seems like you could just, with that ball, I mean, I guess if we had enough of them and we could hit this thing with the ping pong balls, we could get it to stop.
Well,
Especially if you hit it from different directions, too.
Yeah. Why can't you go all the way with the laser?
Well, if you think about it, I mean, these balls light only comes in a certain size, just like these balls do. And so if you consider, you know, the last bounce off that, it leaves it still with some motion, right? I mean, it only comes in little chunks, okay? And that's just the true of light, actually. They're very tiny little chunks, but nevertheless, they're chunks, and that sets a limit, okay?
Oh, wow.
And so, actually, we got into this by studying these processes of what limited you. And so then we knew about some other work that we thought we could use for this, and that's to use turn off the light. Now, once we've got it as cold as we can get it using the laser light, then we turn off the light and we use some new techniques called magnetic trapping, because if you don't hold it, then you got to do something to hold the atoms. We were holding them first with laser light. If you don't hold them anymore, then they go and hit these hot walls and heat right back up. So first you've got to figure out a way to hold them. And so we use a magnetic trap. That just uses the idea that each atom has a little magnet attached to it. You probably don't realize that, but so think about an atom as just like this. Again, greatly magnified.
And that's a bar magnet.
Yeah, this is a bar magnet. Each atom has a little bar magnet. If I come along with a big magnetic field, I can move those atoms. I can exert a force and move them around. So if you make just the right kind of magnetic field, you have to take a bunch of magnets like this, or we go one step better, and we use coils of wire that we run current through.
So you make your own electromagnets.
Yeah, and those make magnetic fields. And really, if you do this right, like we do, it ends up being just like a bowl that the atoms sit in. And so if I can have the next slide here. Let's go back one slide, sorry. Okay, so here's the apparatus, and so what we've done is we turn off these laser beams. They've done all they can. And the blue and green things here, these are these coils of wire. So we now run current through them. It makes a magnetic field that then holds this little blob of atoms just magnetically. If you can go to the next slide. This is sort of this is an illustration of it. You've got this bowl. The atoms have been slowed down from 1,000 miles an hour to a few inches a second, but they're still zinging around inside this bowl, as you can sort of see in the picture. But they're at least held there, and they don't touch anything hot. Now the nifty thing is how you get this cold, and it turns out it's a very, we do it in a fancy laboratory apparatus, but the idea is completely familiar. It's just what happens in your cup of coffee. Right. When you have a cup of coffee, you know how there's steam comes out the top. Well, that steam is the most energetic little coffee molecules leaping out of the cup of coffee into the air, carrying away lots of energy. The ones that are left behind coffee that gets behind gets colder and colder. That's why they put these lids on it. You see, you keep those energetic atoms from getting out. They hit the lid and get bounced back in, and your coffee stays warmer with the lid on.
So that's evaporative cooling. That's why you sweat.
That's it. Yep, exactly the same. You got these evaporative coolers or swamp coolers in your house. Exactly the same physical principle. And that's what's happening. And so we use it here in our magnetic traps. And so we let these energetic atoms leap out, and it turns out the sample just gets colder and colder, and if the atoms don't have so much energy, they can't go as high up the wall, right? So these all just settle down here. As you wait a while, they all settle down here in the bottom of our magnetic bowl, and that's when they actually Bose condense.
Now, since these atoms are like little magnets, are you implying that all atoms are like this and they can get magnetic too?
Yeah, they are. Pretty much any atom has a little magnet attached. The difference between, you know that most things like this chair I don't notice as being magnetic. I have to go get special things like these iron to make it. The reason is that in a normal material, the atoms in the chair or a piece of glass, all these little bar magnets add up in pairs so that one points up and the other points down. They cancel each other out, okay, when they stick together. It's only in a special thing like this bar magnet that they all line up together, and then you see them magnetically. So in here, we don't have two near each other to cancel each other out, so we hold them like that, okay?
Great.
So we've gotten cold down in the bottom by evaporative cooling, and now we need to look at them somehow, though. We've turned out all the lights, so it's all dark in there.
You turn off the lasers.
Yeah, let's turn off the lights in here, too, so we can get a better look at those slides. Yeah, okay. Now, the way we look at them is, let me have the next slide here. What we do is we turn off the magnetic trap that has all these little atoms in it, and the atoms go flying apart. This little cloud here is of atoms down the bottom of my magnetic bowl. I turn the bowl off, think of breaking it. And the atoms then go flying apart. And you can sort of imagine, picture this process, the whole evaporative cooling and this expansion process here is like having a room full of small children. And you know that if you take the loudest, most rambunctious ones out of the room, the whole energy level and sound level goes down. That's sort of like evaporative cooling. Now, the way we look at it, we want to measure that level of energy and rambunctiousness. This is sort of like declaring recess, and everybody goes tearing out across the playground. And now what we do is we take a snapshot. We let these atoms go tearing out, just like little kids. And after a little while, in our case it's a fraction of a second, we take a snapshot picture of that. And you can tell then the most energetic ones have made it the farthest, and the slow, lethargic ones are still piled up here in the center.
Now, what does this snapshot tell you?
Well, it tells us what the speed of what each atom is moving at, okay? And so you can tell how much speed they have and therefore how much energy they have.
So that tells you how cold they've gotten.
Exactly, yes. That
because
tells
temperature
you how
is
cold they've got. Yeah. So in the next slide.
So how do you take the snapshot? I mean, is this photographic film or?
That's just, you're right on key. That's what I show here. What we do is we've got this sample here. I left out here's the picture of my cell again, little glass cell. My cloud of atoms in the middle here, I left out the magnetic field coils in this picture because they're all turned off. So I've got the cloud is expanded out. I take a snapshot. I send a brief pulse of light, just like a flash
bulb.
And that makes a beam of light, and these atoms then cast a shadow in that. And I can sort of illustrate that here if we can turn on this light.
Actually, it's that.
It's that little.
Turn this on.
Yeah, there we go.
Okay. Well, here I'll just use this piece of paper. Just imagine that these atoms block the light in the same way this piece of paper blocks that, and so you see a dark shadow. And what I'm showing in this picture here, if we can turn this light back off, we have a lens just like in a camera, and that goes in. This is a fancy name for a TV camera. So we just look at that shadow on a TV camera just the same way you were looking at the shadow, this paper on a TV camera. Now, Okay.
Oh, sorry, I was in the way. I was casting a shadow.
Okay, so that shadow picture then tells us how hot everything is. Now, if I can have the lights back on. Sorry, let me go to the next slide and show you some of those pictures. These are the real data here, and these are the pictures of those shadows where when this thing sticks up the highest here in the middle, that corresponds to more atoms, a darker shadow. And we've also put in, this is all black and white in the experiments. We put in some nice color because it looks better and it tells you useful things. So what this is the middle here is the things going the slowest. So you can see over here, these are by our standards, sort of balmy atoms. They're down at 200 billionths of a degree above absolute zero. Okay, so we do the experiment, we look at them, then we do the experiment over again, we let them cool off a little longer. Here's one that's cooled off a little longer. Now it's down to only 100 billionths of a degree above absolute zero. Notice there's suddenly this big peak in the center, okay? This is real data. This peak is the Bose-Einstein condensate.
Is this the superatom?
Yes, it really is. All the atoms here are really looking exactly the same. They're all in the same place, like I talked about last time. That's what Bose-Einstein condensation is. And here we've cooled down even farther. This is by far the closest anyone has gotten to absolute zero. It's not quite zero, but it's awfully close. There's nothing but this blob in the middle. Now, you can understand a little better what you're looking at here. I can do an analogy here. If I can have the lights back on. Okay, what we're doing in these pictures is we're turning things off, letting it start to spread out. We take a snapshot just after this happened, and we see how fast it spreads, and that tells you how energetic it is. So the hot ones over here on the left, that's just like taking this water and pouring it out, and you can see if you took a picture just as it hit the floor, that's what you'd be getting over there, okay? Now, compare that with, here I get things a lot colder. In this case, I use liquid nitrogen, frozen air. And now I do the same thing. And seeing this picture, seeing that peak in the center is just like what you see in this, where I pour it out again, and stuff goes flying out. But you see there's a big blob sitting here in the middle that doesn't spread out at all. And it happens just when you get it cold enough.
Wow, so that's basically the condensate. If we were taking a flash photograph of that, that block would be that white portion of the peak?
Yes, this would be this actually blue and white, this big chunk right in the middle that it's not spreading out. It's staying this narrow thing, whereas everything else, normal atoms, go spreading on out. Okay?
Oh.
So that's really the way we make and look at Bose-Einstein condensation.
Cold.
Well, I don't want to hold that.
Yeah, don't pick it up. It's pretty chilly.
One question I have is, you talk about the atoms all being in the same place because they're in the same state, but aren't atoms very tiny? And I think in this picture, although we can barely see it, there's a scale actually attached on there that says the size of that peak is roughly about 1/10 of a millimeter.
Yeah.
So why is that peak so big when the atoms
are the size of a human hair?
Yeah.
The reason it's so big is because as you get atoms colder, they really get bigger. The region in which they occupy, the volume space they occupy, it's kind of these strange laws of quantum mechanics we talk about, but they really get larger and larger and larger. And so in that peak, you see, by making them so cold, we also make them very big. And then what we're also seeing, though, is that they all these many atoms, it's a small chunk, but there's still a lot of them, 10,000, a million, all go into exactly the same place. And so, in fact, the reason they don't spread out there is they're not really separate atoms anymore. It's like they've really have separate droplets that coalesced into a blob. So the best way to visualize this is to really think about, okay, here's normal atoms in a container here, like these little ball bearings, and they're all these separate little guys bouncing around, zinging around. They're hot, bouncing off each other. They're all separate. Now, when you make this Bose-Einstein condensate, it's like you cool these down, and all those things go into sort of one single blob, just like this. And so instead of having all these individual hot atoms, I've got this sort of blob superatom sitting there. Okay. So that's really what caused all the excitement. You know, finally, after 70 years since Einstein predicted it, we were able to see it. And not only see it, but, you know, most physics experiments, you sort of get some data and you look at it real hard, and maybe something's working and maybe it isn't, and you crunch on it and you work some more. Whereas this one, just these big peaks just suddenly showed up right away like that, and they matched everything we
Well,
were
we've got just a couple minutes left, like about 3 or so minutes. So,
Yeah.
is that it for?
Well, yeah, I think that's.
Yeah, I had a quick question. Why don't the atoms just freeze? If you're getting them that cold, why don't they just freeze and crystallize
into a solid.
into a solid?
That was actually the big problem in making this experiment work, is the atoms really, they want to freeze. They know that at these incredibly low temperatures, they're supposed to be a solid. But basically, we use tricks to keep them from getting too near each other and in preventing the processes that allow them to freeze. So it's like it's so-called supersaturated vapor, where you can get this also in your freezer. If you put very clean water in a nice smooth container, you can cool it way below its freezing temperature, and you just touch it then, and it all goes bling into ice, okay? So we've really got the condition of supersaturated, and in fact, they do that. If we wait very long, they go and turn into, get together, and they're stuck.
Okay.
Well, I think that's pretty much going to wrap up our portion of the show. This is by far the most exciting thing that I think we've had on our show so far. And this is kind of a surprise to you, but the Moment of Science staff unanimously voted you Moment of Science Scientist of the Year. So we have this award. So it's an award for Dr. Carl Wieman, Scientist of the Year, 1996. And we want to thank you so much again for coming and showing us this fantastic experiment at what must have been the busiest time of the semester for you. And we really appreciate having you on.
Well, it was enjoyable.
Thank you very much.
Thank you. And if viewers out there, if you want to learn more about Bose-Einstein condensation, check out our webpage. There's links to Dr. Wieman's webpage. There's links to the Bose-Einstein server at Jilla, and you can surf the web and learn more about Bose-Einstein condensation.
And also, once again, there's a typo on that web address. That dash right before my name is supposed to be a tilde. So don't type that in exactly as shown.
And you see copies of all our scientific papers if you're a real masochist.
That's right. That's right. You can read all about it. All right. Well,
all right.
Thanks a lot for joining us for part 2.
And we'll see you next week.